Here we discuss unsteady flows, unsteady ideal flows, and the important concept to remember. So the term that you should associate for now with unsteady ideal flows, and we're looking at external flows, so flow around object. That is the concept of the added mass. And so when we look at unsteady ideal flows, remember those are linked to those are incompressible irrotational flows, but in that case we can no longer say that nothing changes with time, so we have to take into account the unsteadiness, and so the statement of momentum conservation that one would make is the unsteady Bernoulli equation. And remember that the unsteady Bernoulli equation is equal to rho d phi dt, where phi is the potential. This term is the unsteady term, is the only unsteady term in the Bernoulli equation, and the rest are the usual terms, so plus 1/2 of rho u squared, plus the pressure, and plus, we're assuming that the forces are conservative, so plus the force potential phi. And that, remember, for ideal flows, which are again irrotational and incompressible, is a constant which does not depend on time. So you can apply unsteady Bernoulli equation not just along a streamline, but from any point to the flow to any, okay, to any other point in the flow, and therefore this here is equal to a constant. That constant, though, may depend on time. And so we'll look at one particular example of a simple geometry which is accelerating, and we've just discussed spheres, so we'll discuss the ideal flow around an accelerating sphere. So how to think about that? When do you see this problem? You can just think you're having a drink with friends and you're looking at the acceleration of a gas bubble, right? So if the gas bubble is small enough, it will remain spherical, and therefore the velocity of the gas bubble, initially at least, is going to change. So if you're thinking about the frame of reference of the gas bubble, that is like thinking about the incoming velocity, which is increasing, right? So it is not a steady flow, simply because the velocity of the bubble is changing with time. And so what do we have? So we have our glass, and then we have a little bubble which is rising, and so the velocity of the bubble is going to be a function of time. If the velocity was constant, then we would have a steady rise. But if the velocity is non-constant, then we have an unsteady flow. So if the velocity was constant, it would be steady, but the velocity is not constant, and therefore it is steady. Now we have looked at forces on spheres when the flow is steady. Remember, we've just discussed that, and so if you look at a steady flow, and that is, again, the velocity is constant, then the total force onto the sphere is equal to 0. And that is the same reason why for a cylinder, for 2D planar flow, the flow is equal to 0. That is what we call the D'Alembert paradox, because the pressure is symmetric, right? Now, if we consider unsteady flows, it turns out that the force, when you integrate the pressure along the sphere, so we just integrated the pressure along the sphere for a steady flow, but if you integrate the pressure along the sphere for an unsteady flow, then you find that the force is actually not equal to 0. And this is the force which is called the added mass, right? So remember, if you have an external flow, and the flow is steady, and you're assuming ideal flows, then the total force is equal to 0. That's the D'Alembert paradox. And when I talk about the force, I mean the force that you get when you integrate the pressure. So the integral along the surface of your stress vector, which is just the pressure, so minus P on the times the normal vector, ds. When you integrate that on a steady flow, you get a 0. When you integrate that for an unsteady flow, you do not get 0. And remember, this is then the added mass. Okay, so let's take an example. We could take it's going to be the exact same angle, but example, let's think about a wooden sphere. Okay, we think about wood. Wood density is lower than that of water, therefore it will rise and the velocity might change. So let's assume that we have a wooden sphere and that our wooden sphere is and gravity is pointing downwards, right? And you know that it will rise because of buoyancy, but let's not get too carried away with buoyancy for now. If we want to see how fast the ball accelerates, we have to impose Newton's second law. So we have to write that mass of the wooden sphere times the acceleration is equal to the sum is equal to the resultant force, and therefore it is equal to the sum of all of the external forces. So what do these external forces include? Of course, it includes the weight of the wooden sphere. That's number one. So it will be the density of the wood, that be rho W. Oh, that could be rho W is the density of the wood times the volume times gravity. So this is the weight. And then if you think what all the other forces are left, the other force which is left is simply the reaction of the water or of the fluid on the sphere. And so what is that? Well, we need to look at every single element of surface along this surface, along the surface of along the wood water surface. So that means that we have to take our stress vector, which is just the stress tensor times the normal vector, and we multiply by the element of surface ds, and we integrate over the entire surface of the wooden sphere, right? And in inviscid flow, if we're assuming the flow to be inviscid, this simply reduces to the pressure term, right? So that's the only force, those are the only two forces which are exerted on the wooden sphere, the weight and the reaction of the flow, the pressure reaction of the flow. Now, some of you may wonder, where is the buoyancy? Of course, the buoyancy is included into that pressure force. The buoyancy is the force exerted by the fluid, by the water, onto the wooden sphere, and that force is exerted at the surface of the wooden sphere. Actually, it is the hydrostatic pressure term which you integrate. It is not a body force, so oftentimes, as you know, it reduces to a body force, but we haven't forgotten the buoyancy here. At this point, it will become clear later on again, but the buoyancy force is included into that pressure. It's the hydrostatic pressure term within the pressure. Okay, so here is our force, right? This force, in that case, it's quite clear that it only is going to have a non-zero component along the z direction, so let's integrate that. Let's project onto z. And when we project this force onto z, that is what we called the added mass. So that force here, which is the pressure, integrated pressure, is the added mass. Actually, I went a little bit too quickly here. So it is not entirely true that this is the added mass. So we'll discuss it later on. Okay, so the total force here, the total force due to the fluid exerted onto the wooden sphere is this integral of this pressure. And so let me, yeah, it's not really entirely the added mass. All right, and you'll see why. So what is this pressure? How do we get the pressure? Remember, the flow is an ideal flow. Right, so what does this pressure contain? Well, the pressure is deduced from the unsteady Bernoulli equation. Right, so again, the unsteady Bernoulli equation, we have the unsteady term, rho d phi dt, plus the pressure plus 1/2 of rho u squared plus rho gz. So this is plus rho gz, and that is equal to a constant. And so from the unsteady Bernoulli equation, right, we can derive what the pressure is. We can extract the pressure by keeping the pressure on the left-hand side and putting all of the other terms on the right-hand side. And so we get that the pressure is equal to a constant minus 1/2 of rho u squared and this term we'll see later again, but you might recognize that this looks like the term we integrated if we were looking at, this is the term that you would always have in a way if you just had the p plus 1/2 rho u squared equals to a constant, right? When you don't have hydrostatic effects and when you don't have unsteady effect, that's the pressure that you have, and that really represents the drag. And in that case, because the flow is inviscid, you'll see that this term, once you've integrated the pressure over the entire surface here, you will see that that term would give you a zero contribution, again, because it's the D'Alembert paradox. And then you have minus rho gz. That is, once you put that term here, you integrate it into the over the surface of the wooden sphere. You integrate the hydrostatic pressure term, and that gives you the buoyancy. Right? And if you computed this integral, you will get that this is equal to the rho of the fluid, so just rho, times the volume times gravity, and it's pointing upwards. And finally, once you've taken all of the terms here and you've put it on the right-hand side, you're left with the minus partial phi partial t. Right? And when you integrate that term, you'll have a non-zero contribution, and that is what we called the added mass. So that is why the added mass is only there when your flow is unsteady. So when d phi dt is non-zero, and when you integrate this part of the pressure over the surface of an object, you get an added mass. You get a force, which we call an added mass, and you'll understand why we call this an added mass later. I made two sign mistakes here. Sorry about that. I realized this here should be a plus, and that here should be a minus.